Hello everyone and welcome back to the channel. This is Mohammed Talha, and again we're doing an AS yearly past paper to help us practice for our upcoming Cambridge exams. So again, a very recent paper. It's going to give you a good idea of what the examiner is asking, how the examiner is asking things, which is summer 24 paper 23. Without wasting time, let's get right into it. Question number 1. The drag force Fd acting on a sphere falling through a liquid is given by 6 pi eta rv. R is radius, v is speed, eta is a property of the liquid called the viscosity. Show that the base units of viscosity are these. So Fd is a force, and force is the simplest form I think to remember is ma. So that's mass times acceleration. So mass times acceleration, so kg meter per second square. 6 pi I can just leave out because that's a constant without units. Not all constants are without units. Eta is what I need to find the base units for. R is radius, so that's meters. V is speed, so that's meters per second. And then this would become m times m becomes meters square per second. And then I cross multiply to the other side, so that becomes kg meter per second square divided by meter square per second. So kg remains as it is. This is m1, so 1 minus 2 becomes minus 1. S is minus 2. Minus 1 becomes plus 1. So minus 2 plus 1 is minus 1, and I get this form. Next, the sphere has a radius of 3 centimeters, is falling vertically downwards at a terminal velocity of 2 meters per second through the liquid. Drag force is given, calculate viscosity. So I'll just use the expression above. So drag force is 0.096 equals 6 pi, and we need to find eta again. So 6 pi, r is 3 centimeters, right? So 3 centimeters means 0.03 meters, and v is 2 meters per second, and I need to find eta, the viscosity. So I'll just cross multiply here, nothing too fancy with this question. So just divide by all of that on the other side, and this turns out to be 0.085 kg per meter per second, the units that we found in this part. Now it's also important that you start thinking about this beforehand because it's falling at terminal velocity. This means that the drag, which is definitely going to be upwards because it's moving downwards, and whatever the downwards force is, there will definitely be the weight, so they must be equal, because this is what is asked in the next part. The sphere is shown in 1.1. On 1.1, draw and label arrows to represent the directions of the three forces acting on the sphere as it falls at terminal velocity. So I know weight always downwards, right? And you have upthrust always upwards, and then you'll also have viscous drag. I'm going to call that Fd, that's upwards, right? So upthrust is always upwards, weight is always downwards, drag force is opposite to how the object is moving because the object was falling, so it was moving down, so drag force is upwards. Density is given, show that the upthrust is this much. So upthrust is rho g delta v meaning the volume of the object which is beneath the surface of the liquid. So rho is 920, g is 9.81. I need v, but for that I don't have v readily available, but I was given the radius above, which was 3 centimeters. So I can find using the volume of a sphere formula, the volume, which is 4 by 3 pi r cube. Pi r is 0.03 cubed, and when you evaluate this turns out to be 1.0 Newton corrected to SF. Calculate the mass of the sphere. So I have the density and I need the mass, right? So this is just the density formula, right? So mass of the sphere, I have volume of the sphere here. Oh, my bad. This is density of the liquid, right? So for the mass of the sphere, I'll need the weight of the sphere, which I can get from the forces that I labeled. So weight is basically U plus Fd, and now I have both of these. So U is 1 and Fd was 0.096. So I add these to get the weight, which is 1.096, and to find the mass I would divide this by small g. So 1.096 divided by 9.81, this turns out to be 0.11 kg. Let's go on. Define displacement from a point, a kind of definition that wasn't asked a lot, but again we have a question here. So displacement is the shortest straight line distance from a point in a given direction, right? So the direction word is also important to indicate that this is actually a vector quantity. Let's look at part B. An object is projected horizontally at a speed of 6 meters per second from a slope. So this is basically a question on half projectile, because it has no vertical velocity, it just has horizontal velocity. And if I think about the basics of projectile motion, I know that this 6 meters per second is not going to change, it's going to be a constant. Sometimes the examiner also asks a reasoning for this, and the answer is that because since there is no horizontal force, there is no horizontal acceleration, so the horizontal component of velocity stays the same. So the slope is at an angle theta to the horizontal, air resistance is negligible, object lands on the slope a time of 0.71 seconds later and stops without rolling or bouncing. So we need to find the horizontal distance. Now with the horizontals, because this says horizontal distance, it gives you a hint that you'll have to use your horizontal aspect of things. And to be frank, you have nothing about the vertical aspect except for the fact that you know acceleration due to gravity. And with the horizontal aspect of things, there is only one equation of motion which you have, which is basically distance equals to speed multiplied by time, because it's constant. And if you think about it, it's a simplified form of this equation, ut plus half at square. Because there's no acceleration, acceleration is 0. So this entire term becomes 0, and this is basically this expression. So speed is 6, time is 0.71. You multiply this to get distance as 4.3 meters. Now the next part, determine the vertical distance traveled by the object. So if this is talking about the vertical distance, we must use the vertical aspect of things. I know initially it had no vertical velocity, and if I use my sign convention, let's say downwards is negative for no particular reason. So that means that because if I look at the diagram, it's also traveling some downwards distance, so I would also expect that to be negative, because from where it started out from, our reference point, it's downwards from here. So acceleration is negative 9.81. I know the time to reach the slope when it does reach the slope, so I know the time, which is 0.71, and I need s. So the equation of motion to use would be ut plus half a t square. So u, because that's 0, this entire term goes away, so it's half into negative 9.81 into the square of 0.71, and when you work this out, this turns out to be negative 2.5. So you can write this as just 2.5, dropping the negative sign here, because that's just asking for distance. Use your answers in B1 and B2 to calculate theta. So theta is this, right? So let's say it hits the slope here. So when it hits the slope here, I know the horizontal distance it's traveled, which would be this, right? The horizontal distance, which is 4.3, and the vertical distance that it traveled, which is this, and that was 2.5. So I can see that basically this angle would also be theta, right? So this is theta, this is theta. So I can use a suitable trigonometric ratio. So this is opposite, this is adjacent. Let's go ahead with tan. So tan theta is opposite over adjacent. So tan theta is 2.5 over 4.3. So you just use sine inverse to find theta, which turns out to be 30 degrees to 2SF. Next, determine the magnitude of the displacement of the object from its original position. So we found the distances. For the displacement, that's a vector quantity, and I think we just defined this here, right? Yeah. So this would be the displacement, the straight line distance, or 2.5 squared plus 4.3 squared under the root. That would be the displacement. So 2.5 squared plus 4.3 squared under the root, and this turns out to be around 4.9 meters. By considering energy, calculate the speed of the object just before it lands. Now you could have done this using projectile motion as well, but it says by considering energy, so you can't use that anymore. So we know it loses GPE, so mgh, and that must become speed, which is half mv square, assuming no energy losses. However, one thing to be kept in mind is that even when it was launched, it's not like it was at rest. So instead of just using half mv square, I should recognize that because it's the change in height, because we usually write it as mg delta h, this would be the change in speed as well. But if I want my final answer altogether, I can use it like this. So half mv square minus u square, right? M's cancel out here as well. So g is 9.81. H would be the vertical distance that it falls through. Now was it 2.5 or 4.3? So vertical distance was 2.5. So 2.5 equals half. Okay, now whenever we use the energy expression, this is how I go about it. I know that the final velocity, in this case, it would be more. Sometimes it's also that if an object is, let's say it's rolling up a slope, right? So in that case, I know its final velocity would be less. I play around with the terms of this bracket so that the answer is always positive here, right? So even if my final velocity is less, and if my initial velocity is more, I would switch this around so that it remains positive, right? Because otherwise what you would do is you would put a negative sign in front here to show that this is a loss. I don't go by that. I just say that, all right, I've looked at changes. So the change in GPE is the change in kinetic energy. And then I just make the terms work in such a way that both of these turn out to be positive. So the final velocity is what we need, and that's obviously going to be more, right? Because it's losing GPE, so speed would increase, v square, and the initial speed was, I think, 6, yeah, minus 6 square. From this you just rearrange, so 2 times 9.81 times 2.5. That's v square minus 6 square, so plus 6 square, and then taking the square root, this turns out to be 9.22, so 9.2 meters per second. Let's go on to the next one, 3 part A. This says state Hooke's law. So we say that force is proportional to extension produced up to the limit of proportionality. Pretty easy. Part B. So you have a variation of applied force with extension for a sample of material. So force, but extension is in millimeters, right? So you must be alert that this is in millimeters. So I would need to take care of this when I have to do a calculation. The sample behaves elastically up to an extension of 80 mm. So this means that this is its elastic limit, right? I call it EL. And then if I also have to locate this, so the limit of proportionality would be where it's a straight line. And okay, so actually the examiner makes me do this in the next part. And then it also breaks at point X, right? So this is breakage. On the line in 3.1, draw a cross to show the limit of proportionality. Label this cross with the letter P. So this is till where it's a straight line, right? So at 60 mm, this is P. On the line in 3.1, draw a cross to show the elastic limit. Label this cross with the letter E. So let me just, from here, remove the L and make this a cross 80 mm. This is E. Straightforward. Sample in B has cross-sectional area this much and initial length of this much. For deformations within the limit of proportionality, determine the spring constant. So F over X, right? So any force and any extension, as long as they're within the limit of proportionality. So I think the limit of proportionality point was a good one to work with here, because that's, if I just remove the cross for a second, that's this one, right? So at this point, this would be 5, so 5.2, 5.4, and the force is 5.4, the extension is 60 mm right here. So 60 and 5.4. So 60 into 10 to the negative 3, because this is in millimeters, and 5.4. So I just do this. So 5.4 over 60 into 10 to the negative 3, right? And this turns out to be 90 Newton per meter exactly. Young modulus of the material from which the sample is made. So Young modulus is FL over AX. Again, you could pick a point, or you could also be smart about it when you realize this, that I've already calculated F over X, which is the spring constant. So you can also rewrite it like this, that's KL over A. So you have this as 90. The length of the material was given above. Initial length is 3.2, and A is 0.4 mm square. So 0.4. Now just milli would be 10 to the negative 3, but this is squared, so it becomes 10 to the negative 3 squared, which becomes 10 to the negative 6. And then you just work this out. So let's do this together. 90 into 3.2 or 0.4 into 10 to the negative 6. This turns out to be 7.2 into 10 to the 8 pascals. Determine an estimate of the work done on the sample as it is extended from zero extension to its breaking point. Explain your reasoning. Now this is an estimate because you must know that the area under the fx graph is basically going to be your work done, right? But you know this, that this would be an estimate because it's not a formula that you could use immediately, right? So you'll have to count squares, you'll have to count boxes again in this one. This was the reasoning, by the way, when it said that give your reasoning. So just writing that statement that area under the graph would be this. This is your reasoning. For clarity, I'm removing all of this and I'll see what I need. All right. So if I try to do it this way, let's first see the shapes which are forming here. So X is here. Let's try to make this a straight line. Yeah. So what I could do is, I'm thinking this, that if I have this, then I can also drop a horizontal line, find the area of the trapezium, and for the rest of that I can count squares. Because I already saw that this is my limit of proportionality, this is still where it's a straight line, right? So just placing it like this. So I can find the area of the trapezium. So for this, this length, let me just scroll a bit. So this length, this one is how much? So this would be 180. So this is 184, 188, 192, right? So this is like 192. And then similarly, this length is going from 60 to 192. So 192 minus 60, this is 132. 132 here. So these are the parallel sides of my, what do you call it? Of my trapezium. The height of this trapezium, that was going up to 5.4 if I'm not wrong. So the height of this trapezium from here to here, this is 5.4. So let's first do this and then I'll come back and do the counting squares thing. Keeping in mind that the extension was in millimeters. So I'll first do A1, which is half into height, which was 5.4, into sum of parallel sides, which was 192 plus 132, and all of this is with a 10 to the negative 3. So let's first work this out. So half into 5.4 into 192 plus 132 into 10 to the negative 3. This is 0.8748 joules. Then I'll go back here and then I'll try to figure out the area of this, right? So for this, I can see how many squares I have. Again, I'm going to erase this just for clarity. So I have like maybe like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Let's say this is 1, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Let's say this is 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46. So these ones which I took as a square, even though it was less, so I'll make that compensate for this. So 46 and 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, and 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 101, 102, 103. Let's approximate this to like 100 boxes. So 100 small squares. And the value of each small square I'll need to see from the grid. So for each small square, I know that this is one small square right here. So this is 4 mm, and the length of each of these, so this was 3, right? So each one is 0.2. So yeah, 0.2 into 4 into 10 to the negative 3. That's the value of each small square. 100 into 0.2 into 4 into 10 to the negative 3, and then I'll just add. So 100 into 0.2 into 4 into 10 to the negative 3. This is 0.08. So I'll add both of these. So 0.8748 plus 0.08, which is 0.9548. So 0.95 is what I'm getting, right? Again, this type of question where you have to estimate, this is going to take slightly more time than the rest of the parts, and that's fine. If it makes you feel comfortable, then you can do the rest of this and come back to this at the last, because this is just 2 marks, and even if you just wrote this, you still have 1 mark in the bag, right? So it's important that you use good judgment and common sense when you tackle your exam paper with respect to how much time and effort each part deserves. A second sample of the same material has a larger cross-sectional area than the original, but the same initial length. Two samples are each deformed within the LOP. State and explain qualitatively how the spring constant of the second sample compares with that of the original sample. So it's a qualitative analysis, right? So you just have to explain why something is going to be like that. Okay, so because we just use this, we use this expression, right? E equals KL over A, where we called F over X as K. Now I have to talk about how the spring constant compares with the area, because this is constant, right? It's the same material, so Young modulus is the same, length is also the same. So if I rearrange, I basically see that K is proportional to A, right? So that means that a larger cross-sectional area, which is the second sample, has a larger cross-sectional area, so it would also have the same, or it would also have a larger spring constant. So I'll say this, and you should let this reasoning be. You should let this be here for the examiner to see. So you say that for constant Young modulus and length, so you're talking about the proportions analysis that you did here. Spring constant is proportional to area. So you'll say hence the second sample has a greater or a larger spring constant. Let's go on to the next one, which is question number 4. Also a good question. Let me slightly reposition this. So the question says a progressive transverse wave traveling from left to right is shown at an instant in time in 4.1, and you have R and T as 2 points in the wave. You are supposed to state the phase difference between the points R and T. So in very easy way to look at this is in terms of the wavelengths, because I know one wavelength corresponds to like a phase difference of 360 degrees. So I can see how many wavelengths this is. So this to this would be quarter of a wavelength, then this is a half. So this means that the difference between them in terms of the wavelength is 3/4 of the wavelength. One wavelength corresponds to 360, so this would be 3/4 of 360 degrees, which is 270 degrees. On 4.1, draw an arrow at point T to show the direction of movement of point T at the instant shown. So an easy way to do this is basically to make the wave sometime after this position. So if I know that this is traveling left to right, let me just make some of the wave after how it would be. So that means that this peak would have moved slightly to the right, and this one would have also moved slightly to the right. So I can see to be on the new wave, T must be moving down like this. So T is supposed to move down, right? So this is a downward pointing arrow here. Horizontal distance between R and T is 0.62 centimeters, and the speed of the wave is 0.27 meters per second. Calculate the frequency. So I just use this idea that the difference in wavelength is 3/4 of the wavelength. So 3/4 of the wavelength is 0.62 centimeters. So that means 0.62 into 10 to the negative 2. So lambda would be this multiplied by 4 divided by 3. So this turns out to be 0.8333 into 10 to the negative 2. I need the frequency, so I'll just go ahead and use my calculator value with V equals to F lambda. So F would be V over lambda. So 0.27 over 0.833 into 10 to the negative 2. This turns out to be 33 Hertz. Part D. The water wave is produced by a dipper S1 attached to a vibrator in a ripple tank. An identical dipper S2 is attached to the same vibrator. So this means that they both have the same frequency of vibration. The two dippers produce an interference pattern on the water in the tank as shown. Wave crests from each source are represented by solid lines on 4.3, and the wave troughs are represented by dashed lines. So yeah, if you think about the conditions required for an interference pattern to be observed, then it makes sense why they're connected to the same vibrator, because we know that for an interference pattern, the waves must be coherent. So that means a constant phase difference and the same frequency. At point P in 4.3, the wave from S1 has the same amplitude A as the wave from S2. Describe and explain the amplitude of the resultant wave. So this is at the intersection of a crest and a trough, right? So you can either talk about this in terms of the path difference or the phase difference, but the idea is that the waves here are meeting in antiphase, right? So I know this would lead to destructive interference and the amplitude would be 0. So this is what I'll say here. I'll say that both waves meet in antiphase, or you can say meet 180 degrees out of phase and interfere destructively which causes the amplitude to be 0, right? So both of these cancel each other out. All right, but don't just write cancel each other out. You'll have to explain this in terms of technical terms, such as like 180 degrees out of phase, or you can say in antiphase, and they interfere destructively, right? So you have to say this, and then you also have to say finally that the amplitude is 0. Let's go on. State Kirchhoff's second law. So we know that this is the sum of electromotive forces, EMFs basically, equals sum of potential differences around a closed loop. This is important to say. Just like when you would be asked Kirchhoff's first law, so you'll say sum of currents entering equals sum of currents leaving, but if you don't say at a junction, then you would lose that mark. State the conservation law that gives rise to Kirchhoff's second law, so that's the conservation of energy. A circuit contains a cell of resistance R and two resistors of resistances R1 and R2 as shown in 5.1. Potential difference across the two resistors is V, current in the cell is I. And you have to use Kirchhoff's laws to show that the total resistance is given by this expression. So basically the expression for resistances in parallel. So the first thing I would say is this, that in this junction, so if the current I is flowing, this would split up, and let's say this is I1, this is I2, according to the names of the resistors. But I also know that in this case, so I can say that this current flowing in by Kirchhoff's first law would be equal to I1 plus I2. So let me first write that. I equals I1 plus I2, and then if I write this according to V equals to IR, I also know that because that's a parallel circuit, so voltage is the same. So instead of I write V over R. This is the total current, so the total resistance equals V over R1 plus V over R2. You factor out the V's as common, equals V1 over R1 plus 1 over R2. V's cancel out and you get this expression. Electromotive force of the cell is 1.5 volts. When values of R1 and R2 are 10 and 15, PD measured by the voltmeter is 1.3. So this was a question where we had the internal resistance and we have to find the internal resistance for this part. So if the EMF is 1.5 and if 1.38 is being lost across, 1.38 is basically what's appearing, that means the remaining 0.12 is lost across the internal resistance, right? So let me just go back up to this. So R1 is 10 and R2 is 15. So what I can do here is this, that if I have the current, if I basically simplify both of these, if I combine them, so I get the total resistance here, and if I know the current, okay, so I actually don't know the current, I'll have to find the current using the potential difference which appears across them. So I'll get the current and then I can use that for the internal resistance calculation. So first let me just do that the resistance of 10 in parallel with 15, right? So I write it like this, 10 inverse plus 15 inverse. So this turns out to be what? Let's see. This is 6 ohms. And across the 6 ohms, the voltage is 1.38. So if I need the current, which is going to be the same throughout the circuit, because I've now combined those two parallel as one series resistor of 6 ohms. So I equals V over R. The voltage across this is 1.38. Resistance is 6. So let's see what this turns out to be. This is 0.23 amperes. And now if I use this, that basically terminal potential difference is really what's given here, is E minus IR. So 1.38 equals 1.5 minus 0.23 R. So R would basically be 1.5 minus 1.38, which is 0.12 divided by 0.23, right? So 0.12 divided by 0.23, which turns out to be 0.52 ohms. Let's go on. A third resistor is added in parallel with R1 and R2 in the circuit in 5.1. State and explain the effect, if any, of this change on the current in the cell. So if you have another resistance coming in parallel, you would say that the total resistance decreases. Causing current to increase. And then its impact on the potential difference measured by the voltmeter. So again, if I think about this expression, if the current increases, there would be more volts lost across here. So VT, the terminal potential difference, which is what is appearing across the rest of the circuit, that goes down. So I'll say that more potential drop across internal resistance causes terminal potential difference, which is basically so let me write it like this, and hence the voltmeter reading to decrease. Six, nuclei of an isotope of samarium contains 62 protons, 85 neutrons. State the nuclide notation in the form A Z X for this isotope. So X, so this is basically samarium. Proton number comes down here, and on the top you have the nucleon number, which is 62 plus 85, which is 147, if I'm not wrong. This isotope of samarium is radioactive and decays by emitting particles. Gamma radiation is not emitted. Energy spectrum of the emitted particles is shown in 6.1. You have the number of particles, you have the kinetic energy of a particle, and you have to use this graph to explain how this emits alpha and not beta. So this is related to that idea that for a certain nucleus, the alpha particles will have the same kinetic energy, right? Because in that case, what happens is, if I talk about alpha decay, so if I have some nucleus and that becomes another nucleus plus an alpha decay, so the decay energy is shared between these two only, right? So you'll say that in this case, this is why this is alpha, because the kinetic energy of the alpha particle is discrete. It's just one value. Whereas for beta, because it has, in the case of beta negative, there's antineutrinos. For beta positive, that's neutrinos. So they take up varying shares of the energy, which leaves a varying share for the beta as well. And in that case, you have a range, right? So you'll say that kinetic energy of alpha is discrete since there are no neutrinos, whereas for beta, the particles have a range of energies, and that's basically because of the presence of the neutrino or the antineutrino. The isotope of samarium gives decays to an isotope of neodymium. Give the radioactive decay equation for this decay and include the nucleon and proton number of all the particles involved. So samarium was 147 and 62. So SM 14762 becomes neodymium and gives you alpha. Alpha is 42. So you just use the conservation of proton and nucleon number. This must then decrease by 2, and the nucleon number must decrease by 4. By 4. So this becomes 143. A baryon is composed of 3 quarks, all of which have different flavors. The baryon has a charge of 0. 2 of the quarks in the baryon are up and bottom. Determine in terms of the elementary charge the charge on the third quark in the baryon. So you know UCT, this is plus 2 by 3e, right? And the other ones, DSB, are negative 1 by 3e, right? And you now have to, so one is up, which is 2 by 3e. Another one is bottom, which is negative 1 by 3e. So I need another one from here, but they all have to be different. So I can't select another another bottom quark. So it could be either down or strange, right? So any one of down or strange. So plus, I can write like this, plus x must equal 0. So charge of this one, okay, so it's first asking for charge. So charge must be negative 1 by 3e, right? And then the possible flavor could be, so not bottom, so down or strange. So that wraps up this paper. Hope you guys learned something. Like this video, comment if you have suggestions, and share this with your friends. Do subscribe to the channel because a lot more content like this that's going to massively help you in your exams is going to drop soon. See you there.